the other half of the class. Do you guys have some assignment finish? You think before this? No. Huh? What? Later. Ah, I see. What course is that? Oh, MPU. Ah, I see. Maybe we just get started. Don't want to drag too much time. Okay, so thanks to Zhe he pointed out I think in the lecture 4. Okay, so I wrote down the absolute value of e to the power x is equal to the e to the power absolute of x. So this is wrong. You see why is this wrong? Why? Okay. So in other words, if you plug these EX out, right? So this is the counter example. So if you plug this EX out, this EX is really increasing. So the positive X will always be greater than the negative X. Okay. So what is true is the absolute value of e to the power x is strictly less than the e to the absolute value of x. Okay, this is true. Is this true? Less than or equal to, because you have the case. Let me check. Yeah, you have the case where x equal to 0. Okay, so when x equals 0, e to the power 0 is 1, which is the same as e to the absolute value of 0. Okay, less than or equal to. Yeah. Does it make sense? Yeah. Sorry? Oh, lecture 5 is it? Lecture 5? Okay, lecture 5. When you want to prove that EX is equal to the Maclaurin series, you need this. Okay. So this is false for all x in R. What is true is less than or equal to for all x in R. Most of the time is less than, and then there's one occasion where they are equal. Okay. Okay. Another thing I want to point out in the assignment 2. So assignment 2, there's your calculation has no mistake, but you have mistake when interpreting the Fourier series, right? Okay. So we have this Fourier series question of x squared. Okay, let's put fx equal to x squared, where this x is going from 0 to 2 pi. Okay. And then the question says of period. Okay. So first common mistake people do is you think that fx equal to x squared is even. It is even on the whole real line, but it is not even on the interval 0 to 2 pi, right? Okay, so let's plot out what is fx equal to x squared. What's this x squared? So it is even on the whole real line. But what we want to see is just 0 to 2 pi. So we cut around here. We cut at this spot here. Okay, so if you just look at this portion here, it is not, look at this portion here, it is not even, right? Okay, so it's not an even function on this. Some of you, after checking even, so you do the usual finding coefficient, then you found the right coefficient. But some of you, you said that since this is even, Bn straight away at 0 for all. So that's wrong. Okay. So this is not, but, so let me put out the complete statement, but S square is even on the whole real line, but not on the interval 0 to 2 pi. Okay, make sense? Okay, does it make sense for this even part? Question? No question? Question? Okay. Okay. So another thing is after you get the Fourier series, right? Okay. So let's say we already obtained the Fourier series. Okay, let's obtain the Fourier series. Something like that. Okay. So suppose this is the Fourier series you got. Okay. And then you wrote x square equal to this Fourier series. Okay. Is this true? What do you get from this Fourier series actually? What do you get from this Fourier series actually? Okay. So then first you need to ask what is the function I'm asking you to look at here. Okay. So what am I doing here? So let's start over again. So I start with a function from 0 to 2 pi, not touching 0 and 2 pi, but following the pattern of x squared. Okay. First of all, is this periodic or not? If I just draw like this, is this periodic? No, right? Okay. So how to make it periodic? The question say of period 2 pi. Of period 2 pi, meaning we want to repeat this pattern on the interval, every interval 2 pi. Okay. So we keep doing this so we split our real line into 2 pi interval. And then we repeat this pattern here. Okay, let me is okay. Makes sense? So you are finding Fourier series for this particular periodic function, okay, where the pattern is x squared on every 2 pi. Okay. Quotient of x squared. Quotient of x squared. Okay. So remember what we get from this Fourier series. We are using sine wave curve to approximate it. Okay. And then this wave curve is continuous. Right. So you observe that this function here breaks discontinuity. Okay. So what are you really finding? So what you are finding for this sum of sine wave function, you are approximating this curve, right? And then what happened at the discontinuity? Remember the theorem? When we reach every point, it is the half of the sum of the limit from both endpoint here. Okay, so this curve here really, when it close to the discontinuous point, what it do? What it do is it go down and then reach here and then start again. And then go down, start again. And then go down, start again. And then the point above this discontinuity point is exactly the half of the sum of the limit from both sides. Okay, so what you get for this thing, right, is continuous. but it is approximating the curve at 2 pi interval, but it is not equal to the function we have. Okay, it's not equal to the function we have. It's not even equal to x squared. Right, s squared, what is s squared? S squared look like this. Okay, so we actually already modify this x squared. We only get the portion of it and then repeat it. Okay, it's not even this s squared. Make sense or not? Okay, so yeah, so what you can really write, okay, what you can really write is, what you can really write here is the Fourier transform, Fourier series of our f. Okay, so this f and this f here, right, slightly different. Okay, slightly different. Okay, why? So f here is just this fx equal to x squared, right? So you should ask why I can put f here. Okay, so by what? Hmm, by construction. Okay, by construction. Given this f here, we can construct this f. Okay, because okay, sorry, I should let me draw another diagram. It's easier. So what we started with the fx is actually just this bit here, okay, 0 to 2 pi. This is the fx we have, okay? But we do the extension, okay? Extension, then we somehow also call this fx as well. So we just put f, okay? Don't create too many notation here because we already know that from this construction here, we are repeating the, okay? So you need to be aware what we are using. Okay. So there's something going on between these two f here, where we extend the pattern. Sense? Does it make sense? Okay. So putting x squared here is definitely wrong because x squared means something like this. Okay, on the whole real line. So you can see that this green line here doesn't match this green line here, right? Make sense? So the Fourier series you get, right, is something continuous. Okay. So what does this Fourier series have to do with the original function? Okay, it approximates the graph at the 2 pi interval. Okay, make sense? Make sense? Okay, so that's why we introduce this new notation here. Capital F subscript F. Okay, we don't even put fx here because they are really not equal. You can check on the discontinuous point, right? So Fourier series have something in the discontinuous point, right? So they are not equal. Okay, so you also cannot write fx. Okay, the only right way to write is Fourier series of f. Okay, this is the discrepancy between f and Fourier series of f. Does it make sense? Make sense? So how about I create another graph for you? So let's take this bit out. It's stuck. So let me draw the process out. So okay. So what we do is first we got this f here, and then we extend to this, and then we do the Fourier series. F subscript f. Okay. So you can see that these two might not be the same function. Okay. Make sense? Question? Question? No? Okay. Hey, where is y again? You on the way. A bad habit. Really bad habit. Huh? What? Say again. Oh, what? What, you got exam today or no? Ah, so you see, time management is very important. Okay, please manage your time well. Okay, so this is the business with forest series. Any other question? Okay, so yeah, okay, okay. So let's recall the idea of limit again. Okay, let's recall the idea of limit again. Let's start from okay, last time we discussed about RKs, right? Okay, continuous function of one variable of continuity. Okay, so let's discuss about continuous function of on two variables. Okay, so we have x, y, and z. Okay, what is the limit to this point A, B? Does this limit mean? So we want to study the limit of f x x x y to a b, okay, of let's call this graph fxy equals to L. So what does this mean? If for every epsilon greater than 0, there exists a delta greater than 0, okay, such that if uh, we can find point that is delta close to AB, then what? Then the value of xy and L is arbitrarily close. Okay. So what does this mean? So I give you a so let's put down the step here. So I give you a delta first. Okay. Let's see what this delta is controlling. So let's look at this delta. Where the delta controlling? The delta is controlling the point around F around where? Around L. Right? Okay. So let's say this is our L. So let's say this is our L. So our L is here. Okay. Let's say this is our L. Okay. Make sense? Is it okay? Okay. Let's say this is our L. So we want to see around delta around this L. Okay. So what color is better? Use. So around this L, we look at the delta difference. Not that we look at the positive and negative difference, right? Because we are taking the modulus. We don't care where it's approaching. Approaching from above also can, approaching from bottom also can. Okay? As long as it is approaching that. And then we want to see that if we can find some xy around AB, okay, around AB, such that fxy is epsilon close to it. Okay, make sense? Okay, so let's do something crazy on this graph. So maybe we go from very far, come back, and then touch it. Maybe go up again and then come back. Okay. So yeah. Okay. So what's going on? So can you within this epsilon, right? Can you find fxy, there's this epsilon close to it, and then there's some xy that give you this point. Okay, what are these points here? What are these points here? So what are these points? So let me see. So what are these fxy point referring? If you look at this diagram here, it is the part on the top of f. Okay, let's call this point a name. So this point has a name is FAB. Okay. So we look around FAB. So we look around FAB. So these are the point we are talking about. Okay. And then these correspond to some point in the XY plane in our domain, okay, which is delta away from our AB. Okay, does it make sense? Make sense, huh? Okay. So because this graph, right, I didn't show you the 3D how's it, the 3D depth, right? You cannot see whether it corresponds to which point at the 2D. So I can only give you a brief outline here. It's around here. Okay. Does it make sense? Because you don't know whether the line is, because you don't know whether the line is like this or something like that. Okay, depend on what x you correspond to. Okay. Okay. So why I bring this up, because we're gonna learn the partial derivative. So what's the partial derivative? So last time where we stopped. So we stopped at this definition here. So the partial derivative of f with respect to x at AB, okay, is denoted by f subscript AB, where we study the limit again. Okay, what kind of limit we are studying? We are studying the limit where f of a plus h, comma b minus f ab over h. Okay, so what I want you to appreciate here is derivative is a limit of another function. Okay, seems like this function tells you something on this function. Okay, this special function here. So I'm talking about this special function here. When you study the limit, okay, it tells you something about the original f. I want you to think of this partial derivative this way. Okay. It's a limit of another function. Okay. So what's a partial derivative of a function? It's a limit of another function. Okay. So why this function here makes sense? Okay. So last time we talked about the 1D case, right? Okay, one-dimensional case. So last time we talked about one-dimensional case. This really starts from this straight line here. Okay, how we define the gradient of a straight line. This definition, this limit definition here really comes from here. Okay, so how do you find the gradient for a straight line? Okay, you can fix any 2 points on the straight line. It gives you the same gradient. Okay, so this is an invariant of this straight line. Okay, that's why we are interested in it. You know what I mean? So if you pick literally any 2 points on the straight line, and then you do this construction here, so let's call this fx. So if you take fx1 minus fx2 over x1 minus x2, okay, you get a number, right? Top are the difference of two numbers. Bottom is also difference of two numbers. So this number divide number, you get another number. Okay. So this number wouldn't change if you pick any 2 points on the straight line. So this is called an invariant of this straight line. Okay. So in mathematics, often we look for some invariant to study. Okay. So this is an invariant of this straight line here. Okay, so how we extend this idea? Okay, so how we extend this idea to something that's not straight, right? Okay, So we can somehow learn eh, so what we can do, what can we do? So we try to use more straight line to approximate a tangent line at any point on the curve. Okay, does it make sense or not? Does it make sense? So how to say? Let me think. Should I? Okay. Yeah. So we study how this tangent curve here. So let me how about drawing this. So this curve is not as nice. When the curve is not straight, right? Okay, you cannot simply pick two, right? Because you will like slice in between the curve, right? But what you can do is you can so okay, so first of all, so let's fix some uh destination we want to get. Okay, for example, we want to get this as our tangent line at, let's call this AB and then FAB point. And this is the full coordinate. Okay, so how to get this straight line here? Okay, what you can do is you study all the straight line near to this point. Okay, so you keep doing this as close as possible, as close as possible. You can see that this line here will eventually approach to this horizontal line. Does it make sense? Does it make sense? Does it make sense? So this is what this definition is doing. You see, consider the line or the line near to it. So you plus your, so you consider the point that is near to this AB. Okay, you consider the point near to this AB, and then you will get a different edge here. Okay, okay. So let me give you an axis to imagine. So this is our. Okay, let me do some cheat here. Okay, let's put this as R2. Okay, for my easy explanation. I collapse the plane. So you can see that this is AB. Okay, and then these are something close to AB. So maybe I call it A, sorry, maybe I call it A plus 0.5, B, maybe, okay. Another point, I call it A plus, sorry, this one, A, hmm, so let me point out this point here. So maybe I call this A plus 1, B, okay, and then so on, okay. So we're going from far to close to this point, and then we study how this line change. Okay, eventually, can you see that this line will eventually limit to this tangent line here? Can you imagine? Okay, so this is what we are doing. We are taking the edge as small as possible. So we are getting closer, closer, and closer, and closer. Okay, 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 we're good. So so what? Yeah. So the moral is I don't want you to think about differentiating a function is like differentiating x squared equals to 2x. Okay. I want you to think about what you are really doing is this limit definition here. You are considering a limit of another special function. 哎，
是有问题
啊，
然后中间有问题哦，马上
啊
马上set，
alarm again. Okay,
还有 I think
okay, okay. If you are late next time, you need to trick everyone in class.
okay, no problem.
Okay. No. Okay. Okay, sure. So we are talking about partial derivative now. Okay. So yeah. So the idea is when you every time when you do derivative, right? I want you to think about you are taking a limit of a special function. Yeah, this special function define an invariant for your curve or straight line. Okay. So this is kind of interesting because you just start from this simple piece of information and then we grew out a few called differential geometry. Okay. So we are just looking at this particular small number here. Okay, so next, just now we look at the derivative with respect to x. Now we also can look at the derivative with respect to y. Okay, so when you look at the derivative with respect to y, typically you only change the distance between the y direction. Okay, you look at the change of the y direction. Because in one variable, right? One variable you only have one direction to change. Okay. Now you have two direction to change. That's why we call partial. Okay. We just look at part of it. Okay. X or Y. Okay. Of course, if you want to look at any other also can. Okay, but we are not dealing with it. But for now, we only look at the X direction and the Y direction. Okay. Okay. So not that these two okay, let's do some checking here. So for example, let's look at this formula here. Okay, what is the fixed variable here? Okay, so many symbol here, right? These symbols are variable, so what variable are fixed here? Let's talk about this first. Which variable are fixed? So first identify what variable you have. You have f, you have a, b, you have y, you have h. Okay, so there are 1, 2, 3, 4, 5, 5 of them. Right. So which are fixed? So I break into fixed variable and let me call it indexing variable. I can't find the I'm not sure if I can find the right word, but let's call it fixed and indexing variable. So one is a running variable, one is a fixed variable, is a given. Okay. So what are the fixed variable? In this definition here, what have to be given first before you can do computation? AB, okay? So you need to given a point first, okay? So you should think of AB as some point. For example, uh, 1, 2, okay? Any point, okay? What else? Any other fixed variable? X, where's X? X is not in here, right? So we are looking at this particular equation. Okay. So what else? F, right? F. So f is a function. So you need to start with one function first before you calculate stuff. Okay. So you start with one f, one ab. Okay. So how about h and y? Yep. Hey, very good. This is the good question. Okay. So before you answering this question first, you need to understand what I say first, right? So why I put this fixed and indexing variable. Okay. So as a math student, right, you should ask what's the definition of these two. Okay, so what's the definition of these two? Right. So what's the definition of these two? So I define my own definition. Okay. So what's a fixed variable? So a fixed variable means a single. Let me think how to write it. So a fixed variable means a symbol which which is associated a fix a particular element in the set. Okay. Does this definition make sense to you? So this symbol is associated to a particular element in some set. In the set. In the set. In the set. In the set. Okay, in some set. So it is associated to some value. Okay, so for example, this function here is a particular function uh, in the space of continuous function of two variables. Okay, and then AB is some particular point in R2. Does that make sense? Examples, examples. Okay, examples. So examples. Okay, good. So right, that's right. So you need to have examples, right? So for example, here, this AB, right? So I say that AB is a fixed variable. Okay, so why? Because I can associate it to a particular element in the set of R2. Which can, which can. Hmm. Does this make sense? Yeah, yeah, that's right. That's right. That's right. Okay. So how about indexing? Let's give this definition. I create my own definition, so maybe we need to check whether it makes sense or not. So what's the indexing variable? Okay, it's also a symbol. Uh, what's the symbol? Which is associate to the symbol which is associated to what's this indexing symbol should say? Which is associated to and I think I will introduce some contradicting definition here. Did I say this? Which is associated to and let me write down what I want to write first. All the set. Not all the set, you know. That's it's a symbol. What should I say? Hmm. Try to put it. I wanted to say it's a rounding variable, but it's not well defined. Hmm. How about I fix it and then I let you know again next lecture. I fix the definition first. Uh, Let me see. How about we take a break? Okay, after a break, I fix this definition. Take a break. It's okay. Earlier break. And then I fix this definition. I think we have to get this done before we continue. Otherwise, it will be be disaster. Okay, let's take a break, 10 minutes. And then within this 10 minutes, I get it done and then we continue. Okay? But
variable 跟 indexing variable 就是你的 AB 啊，就是你的 fixed variable。indexing variable 是你的 H 不是
so
？H 是 H 不是？indexing 是 H 不是？
我要讲 H，but 但是我不知道。呀，对，我要讲的是 H。
这边
希望这样讲。
如果我们这边直接不要定义这两个东西，我们就讲 AB 就是 given，然后
what is given and then what is 什么呢？另外一个叫什么？
另外一个就是因为你的会是一个 approaching limit 嘛，所以你可以 approach 到这个 arbitrary 的是
可以，I mean 我是讲那个叫什么东西，我现在要讲那个东西叫什么，但是我忽然间我等下也 try 去找，and then
我们 first one 应该没有定义过。
没有，我只是要一个比较就 I mean foundation 的东西吧，但是我现在忽然间 recall 不到那个词，我想想那个东西，等一下啊，如果你什么 suggestion 你再跟我讲。
不过我想得到 AB 就是 fixed 进去 given。
对，I mean 我想现在又有一个特别词，但是我现在想不到那个特别词，Let me think，等一下啊。 So let's start all over again. Spend 1 hour talking about this abstract definition here. Okay, it's okay. I think it's worth. You guys know how to calculate, right? We can skip some calculation. So this one is important. So this is really important. Okay. So we change our terminology. Don't use my terminology. So use this more common one. So they use free variables and bound variables. Okay. So what's a free variable means? So a free variable is a variable whose value must be known in order for the whole expression to be evaluated. Just now we already talked about this, right? So we say we must know what is f, what is the point, and then we can put it into calculate. Okay, so this is called a free variable. What is a bound variable means? So bound variable is a variable occurring within the scope of a quantifier. So you already fix where it has to happen. Okay, and so no longer available for substitution by a constant. Okay. Remember last time we talked about the Fourier series stuff? When you multiply the cos m pi x and cos n pi x, right? So n is already running from 0 to infinity. Okay, but n is something that is free. Okay, yeah, okay. So in this question here, so in this equation here, okay, so what are free? So f, you can substitute any function you like. Okay, you can put in any function you like. Okay, and then point, you can look at any point, any function at any point. Okay, and then y, you need to differentiate, you need to determine whether you want to go from the x direction, or you want to go from y direction, or you want to go from different direction. Okay, then these three things together, okay, put together, and then you compute the limit. So you compute the limit, and this h here is already controlled. Okay, so this h here have to be in real number, and then the extra condition of this set is you want to take limit from positive or negative towards 0. Okay. So everything here, only h, I tell you what to do with them. But for the f, for the point, you have to decide yourself in order for this expression to make sense. How about the others? How the others? Please, one thing to note here. Please don't confuse with the word here. Don't put your own interpretation to free and bound, because what we are focused on is the thing at the back. This is the trick of learning these definitions here. Okay, because people tend to put their own thought when they first see this free variable or bound variable. Okay, you tend to put your own thought into it, but no. What I want to focus here is at the back here. This is really what I want. So I want a variable whose value must be known in order for the whole expression to be evaluated. You must know this sentence first. Okay. You can call it free variable, you can call it non-free variable, you can call it apple also can. This doesn't matter. Okay. So this name here doesn't matter. What's matter is what is at the back. That when you study definition, this is what you need to study. You need to study what they want. Okay. The name here, I can put anything. I can put orange also. And orange is a variable whose value must be known. Okay. So why we put free variable? There must be some reason. So that's that reason you can think afterward. But first, you need to get what I want here. Free variable, I want a variable whose value must be known in order for the whole expression to be evaluated. Okay. This is the thing I want you to know. Make sense or not? So I mean, I'm telling you how to read definitions. Okay, the definitions, the most important part is the after is, not before is. Okay, after is the most important part. Before is, you can name it anything you like. Okay, depend on how you phrase the definition. Maybe the name is before or after the is, right? Because I also can say a variable whose value must be known in order for the whole expression to be evaluated is called a free variable. Yeah. So the the terminology of the definition is not important. What is important is the object you really want to look at. Okay, so the object I really want to look at is a variable. Okay, so you need to differentiate object and adjective in mathematics. Okay, so object here is a variable. Okay, another object is also a variable. Okay, so we got two variables. So what's the difference between these two variables? So this adjective become important now. Okay, although this adjective is a bit long, but anyway, we have to deal with it. Okay, so there are two variables here with two different adjectives. Okay, apparently these two adjectives enough to differentiate all the variables you want or appearing in mathematical expression. Does that make sense? Okay, so in mathematics, right, you have object and adjective. Okay, first you need to identify what adjective first, and then you identify what. You have to identify what object first because you need to start with a thing. Okay, and then you start with describing this thing. Okay, this is how you read the mathematical stuff. Is that okay? Yep. Question. Because why here? When I think of this y, right, I can substitute this y as x. Okay, let's say we already fix here, then maybe we go down here. Okay, I think you are right. Maybe in this case, we should put it here because we only look at this particular fy. Because I was thinking you can see from different, different directions. So I think in this case here, this should be y, right? Because if you fix y, then this is how you put your h. Okay, if you fix x, then you need to change the different way to put your h. Is that right? But so y is a bound. Okay, how about let's decide what y is a bound variable or free variable. Let's decide bound or free. Bound or free. So y is a bound or free variable. Let's decide. Even these two definition here. Bound or free. Who support free? Why is it free? Why is it free? So you mean I need to know it is y or x first? This is what my stand is just now. Okay. So I mean, so do you mean that in this case here, so in this case here, okay, I think we are doing something abstract at the back, right? Okay, so let me resize this. I mean, okay, let's go to some foundation next here. So I mean, okay, let us call this phi. Okay, let's call this phi a new subscript phi. Okay. So what's the difference between differentiating with respect to x and y here? Okay. So the only thing changed is this part, the front part. Either you put hash on the x part or you put the hash on the y part, depend on the subscript, right? Okay. So maybe we can define this guy here. So f, maybe I put, this is a function of f, a, b, and h, and minus f, a, b over h. Does this make sense or not? Does this fee make sense? Okay, let me change something. So how about I change to another thing? So okay, so fee here takes in value x or y. Okay, and then we have this capital fee here. So this give what? So this give f of a plus h b, or f of a b plus h. If sorry, I need to get another variable here, so it's fee. If fee equal to x, if fee equal to y. So y is free or not? Is the value must be none in order for a ring. I think we don't need to go into that. Okay. So what's your stand on bound variable again? Occurring within the scope of the define. So there's no quantifier on y, right? Yeah. But in this case, it is a bit weird because y is just y. Because for function, we can pick any function, right? But here, y, here only one choice. You can do. So we stick with free. So we stick with free. Does anyone else thought the thought? So y here, we need to put y here. So for the expression to make sense, okay. Like there's no quantifier for y. And or maybe are you saying that it's no longer available for verify the constant? Maybe your point is here, but there's no quantifier here. Confused, Means you confused. Not following. Okay. Yeah. I mean, we should start with the definition before the stuff. Yeah. Otherwise, we start from different stand, then we can't reach the conclusion. We have to start from one place. Okay. So put it as free. Free. Okay. So if anything's wrong, we can discuss again. But the point here is I want you to know what variables are given. Then, like Ming Xiu said just now, what are given? What are given, and then what are found here. So how to say? Yeah, I cannot say much. You need to think about this concept, and then this concept will slowly sink into your mind. Okay. I think there's a reason why they put free, although it's not quite free, to make these two variable opposite to each other. One of them is called bound, is quite reasonable because we are bound within some set. But the other, what do you want to call it? I mean, yeah, never mind. I don't want to say much, comment much. So remember is one kind of variable is you need to substitute for the whole expression to make sense. The other is it's already occurring in some with some quantifier, and no longer for you to substitute as you like. Okay, you cannot simply substitute this edge anymore because this edge is get control. Okay, for A, B, F, you can decide what you want to put. Right? You can study any function you like. You can study the function at any point you like. Okay. Yeah, this Y here, right? I think we cannot talk about it in this context here. I think this Y cannot talk about. I think we cannot talk about this Y in this context. Maybe I'm not sure. So let's put this as a box first and see how we can do it. Okay. 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 So why I do all this troublesome stuff? Because next we can see partial derivative as a function. Okay, sorry. What's going on? So why I do all this troublesome stuff? So instead of looking at a particular point, we want to understand this AB, this partial derivative as a function. Okay, so you look at all the point. Okay, you look at all the point and then see how this point changes. Okay, so these xy are bound now. Okay, it's bound variable now. It's not free variable anymore. Okay, make sense? Yeah. So these two things are not the same. I'm not just substituting AB with xy. Okay, please don't think like that. This is a function now. Okay, this, I think this is just a number. This, what you get here is a number. Number. This, what you get is a function. Okay. 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 So next, there are few notation you can write. You can write f subscript x xy, or you can write f xy or del f over del x. Okay, so we don't use this dx anymore. Okay, because this d usually denote we only have one variable inside. Okay, so if del is a partial, so we might got more variable inside. Okay, so this is called a del f del x over del x, or this is the right. This is the accurate way to write. Last time I mentioned this, right? Okay. Or you can write del z over x. So what's z? So if we write z equals to f xy, okay, we can write del z over del x. Just like what you learned in the high school, you let y equal to x and then differentiate y with respect to x. Okay. So this one. Or we can write capital D subscript f subscript 1 and then f. Okay, 1 usually 1 is x, 2 is y, and then 3 is z. Okay, this 1 2 3, right? How we make this connection? Because we follow the orientation. Okay, we first add the x-axis, and then second we add the y-axis, third we add the z-axis, and then follow the right hand grid rule. Okay, so you can do it for higher dimension also. Or we just write capital D subscript x. Okay, and then you will see all these happening across the mathematics literature. You can see all sorts of these notation that all means the same thing. Okay, so let's point. So how to find partial derivative? So let's say we want to find f subscript x, right? So just now we said that we need to fix the y. Okay, we need to fix the y. So we regard y as a constant and differentiate fxy with respect to x. And let's see how we do. Similarly for fy, okay, we regard x as a constant. So let's see how we do. So we start with fxy equals to x squared y plus 3y cubed. Okay, so formally or classically, you should go through the limit process, right? You need to go through a limit process. But in this case, we just play some cheat. So there's some cheat here. So we don't do that. Okay, so what we do, so we just use the modern way to compute the different derivative. Let me see. Okay, so we do some shit here. Okay, so what we do, so let's say we want to compute this function with respect to x. Okay, so we need to treat y as a constant. Okay, treat y as a constant. So y is already free. Okay, y is already free. So we treat y as a constant. So what do we do? So let me write. So treat this part as a constant. This is not a rigorous way, but this is a way to calculate. This is just a way to calculate. It's not a rigorous computation. So if you have a constant multiply x squared, you want to differentiate the x term, you just get 2x y. Okay, x times 2 constant, 2 and y. Okay, and then you differentiate a constant without x, you just get 0. So you get 2x. Okay, so let's say you want to do it formally, right? So you need to check that this is equal to the limit of that special function. When you compute you want me to write it out. So formally is what I won't do the computation, but let me write out for you what you should be thinking about. So this is formally the limit of h equal to 0 of because your f, okay, so let me write out f x plus h y minus f x y over h. Okay, so this is the definition, right? Let's check. Yeah. Okay, and then you need to do this computation, this huge computation here. So our x is x plus h squared times y plus 3y cubed minus x squared y plus 3y cubed. Okay, so it turns out that this limit of this guy here is just 2xy. Okay. Yeah, this is formally, okay. If you are interested, you can do it. You will do it at some point, but not here, I guess, not here. So how about differentiating with respect to y? Okay, what do you get? So you need to treat x as a scalar. Okay, and then you differentiate with respect to y. So what do you get? You get x squared plus 9y squared. Okay. Okay. Have you guys seen partial derivative before? Or do you already teach her?
But I don't teach the reason.
Reason is what?
The definition.
Oh, the definition.
Know how to do.
I thought you guys have proof. No proof? Oh. No proof. So he do calculation, so I can skip calculation now. Okay, never mind. I just do it. Okay. Yeah. Okay. Just do it. Okay. Yeah. So, so so this is yeah. So this is the yeah. This is the thing I want to say, and then what you do, the question not only want you to find the derivative, you also need to evaluate the derivative at that point. Okay. You need to evaluate the derivative at that point. So after you put in the number, what do you get? 1 times 1, 2 times 1 times 2 is 4. And then similarly, fy of 1, 2 is 1 squared plus 9 times 2 squared, which is 37. Okay. Similarly, right? We introduce two partial derivatives. So one partial derivative is at that point and also as a function, right? So similarly, this number here, right? This number here also can compute in a limit way. You see it? You see it or not? I write down the limit way. So let me write down the limit way. Remember, we substitute our x to a particular a and b. Okay, in this case, this a and b is a real a and b. Okay, so this example is exactly exactly demonstrating what I said just now. Okay, so this is a real life. Okay, I consider it as a real life. My life is mathematics, so this is a real life. So this what is this? So a here is 1. Okay, so f1 plus h, b is 2, so minus f1 plus 2, so over h. Okay, so you can see that what we do here, see, all the free variable become a real things. You see why I differentiate these two variables now? Okay, so you see this f a become a real things here. Okay, becomes a real computation stuff. So let me put it here. 1 plus h squared times 2 plus 3 times 2 cubed minus. Okay, I think I left this limit as your exercise. So try and convince yourself they are the same. 1 squared times 2 plus 3 times over h. Okay, can you see? Can you see here? You see, these are h doesn't change. Okay, so this h doesn't change. Okay, but all the f a b here all become a real number, and then f become a real function. Okay, this is why I differentiate these x, y terms here. Okay. Yeah. Okay. So it's a good exercise if you can see this limit as actually what you get on the left hand side. Okay. Okay, let's skip the next one. Hey, what time we finish? 1. Okay, we still got time. Okay, let's skip this example here. Things you also already done some calculation before. Okay, next. So next, what are these partial derivatives in a geometric way? Okay, what is it in a geometric way? So they are the slope to the curve of C2 and C1 at the point PABC. So what are the C1 and C2, right? So this curve, right? This curve should follow along. Okay, so let me write out here. What is this partial derivative referring to? So they talk about the dx and dy. Okay, so dx and dy. Dx you differentiate along the x-axis. So you have a surface. Okay, you have a surface. You can look along the x-axis. All the x-axis, what is happening? Maybe just look at this picture here. So you can look along this x-axis. So along x-axis is this way. Okay, what is happening to the gradient, right? Because we know how to find for the curve, right? Okay, so similarly, you do it for the surface. You look at one line, okay, and then for the y-axis is on which way? This way, okay. So you go along this way, okay. Make sense? Okay. But now we want to fix a point AB. So AB is here. So you look at the one that move along x-axis and the one move along y-axis. Y-axis is this way, x-axis is this way. Okay. So T1 correspond to the dx and then T2 correspond to the dy. Okay, make sense? Make sense? Question? Okay, okay. Okay, so far okay, nothing special here. Okay. Sometimes partial derivative may be interpreted as an instantaneous rate of change. So this is an application. So what happened at the point instantaneously? Okay. So let's I don't want to teach this one. Let's check if you can do this computation. Is 伟泽 here or not? I don't know about 伟泽. Oh, 伟泽. Okay. So what is partial derivative of this f with respect to x? So given you an f, right? Given you an f. So what's the s partial derivative of this x? You know how to compute? Minus 2x. So how minus 2x? So how you compute this? How you compute this? Hello. Yeah, here. Okay. Sure. Okay, as long at least you're willing to say, but please also learn English, okay? Yeah. So you mean the others are treated as a constant, okay? 常数 is constant, okay? So you treat that as constant. So you differentiate the constant, you get 0. Correct? Is it correct? Correct? Okay. Yeah, okay. So you get minus 2x. Yeah, really, you need to brush up with your English because later you need to do internship also, right? You need to do internship, so yeah, this is a good place you can improve your English. So how about differentiate with respect to y? Let's get that one. Huh? Let's get that one. Uh, if any one name I can remember. Tần Ye. Who is Tần Ye? Oh, Tần Ye. Okay. Minus y. Y. And then okay, good. Okay, good. Very good. So this is the way we teach in the class. So I teach you two way, right? One is the limit way, one is this treating constant way. So yeah, so these are the two ways you can use. Okay, good. So hey, hello. So what is the so you can see that these two are partial derivative as a function. So meaning you can see that if I put different point into it, you might get different values here. Okay, in particular, we want to look at the partial derivative at 1. Okay, 1. So 1. So with respect to the direction of x, what do you get? Minus 2. Okay, with respect to the direction of y, what do you get? Minus 4. Okay, so what is minus 4 minus y means? So if I plot z against x, okay, if you don't like z, I just put fxy also can. Yeah. Maybe we put z better. Okay. Extra the height, height what? Height function, height coordinate, and height coordinate. So both of them looks like what? Is this kind of line, right? Is the line that goes through the second and the fourth quadrant. Okay, so this is the gradient. Yeah. Okay. Make sense? So, but our our picture living in 3D, right? So you need to put these two together. Right, you need to put these two together. So how you put these two together? So you need to first start with your 3D coordinate first. So we have our X here, our Y here, our Z here. Okay, so you can put them together by referring to the arrow. Okay, so you can imagine this 2D picture here stacked onto here. And stack. You stack it. You take this piece and then stack it on this picture here. Okay, so do you see the right direction or not? Can you see the right direction? If you match these two and arrow here, can you imagine? Does someone can't see it? Hey, you can't see it? Can you see it? Zoom. I'm not sure how to zoom. Okay, maybe I put side by side, then I can zoom. Now I can zoom. Okay, so you first match these two together. Okay, I mean match to this 3D model, and then you can see that this direction is the same as this direction. Can you see it? And then really you need not origin now, you need to place it on 1 here. Okay. Okay. Can everyone see? Okay, good. Okay. How about this one? X1. Is it the right place? Okay, right direction. Okay. 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 Yeah. Okay, good. Do you want to see longer or okay already? Okay. Okay. So how to say? So you can see that from this tangent line, right? You can somehow recover your shape, isn't it? So this line here follow the uh follow the surface. Here's the point on the surface. Okay. So sometimes we study the geometry or the shape. Maybe we don't know how to draw it. Okay, but if you can write it algebraically, you can differentiate it. Then somehow you can use these the changes of this tangent line and try to draw the everything out. Okay, because harder surface, right? You don't have like polynomial function anymore. You don't have like ex something like that. Don't have the standard shape anymore. Okay, so what you can rely on is you look at this how this tangent change. Okay, yeah. Next. Okay, so do you know how to do implicit differentiation? No. Okay, so let's do once. So how to do the implicit differentiation? We didn't explain why it is true or why we do this, but what we do is to differentiate an equation, okay, equation with a different variable, we can do implicit differentiation. So we differentiate both sides. We differentiate both sides with del. For example, if we want to find del z, del x, we differentiate the equation both sides. Okay, because in principle, right? In principle, you want to write. So let me say, in principle, you want to write z equals to something blah blah x y, yeah x y, and then you do differentiation. But in this case here, you have you. So in this case here, you have this z cube z. Sometimes it's hard to factorize the z out. Okay, so we can do implicit differentiation to get what we want. Okay. So what we do here is we just differentiate every term, okay, every term in the function. So what do we get? So we differentiate s cubed because, okay, so why we can split it? Actually, we need to say that this del here, right, is a linear operator, okay? So derivation are all linear operator. We want it to be a linear operator so that we can do this convenient stuff. Otherwise, we can't split it. If we can't split it, then this is a trouble. Okay, so if we can split it, then should it be easier? So what we get is 3x squared plus there's no x here, right? So we get 0. How about z? Because z, this function, right? This function of z is in terms of x and y, actually. Just that we cannot split it up. Okay, so there's something. So this z is in terms of x and y. So we need to use the chain rule. So we get 3z squared of del z over del x. So here we use. So let me write out the real reason why. Okay, so we use chain rule because z is of x and y. Okay, just that we cannot factorize it. Okay, one thing is in your assignment, right? In your assignment, some of you also do like this. Okay, you can, but I encourage you to put into words. Okay, like what I did in my solution. Have you guys looked through my solution or not? Yeah, try put it into words. Okay, I mean you can do this, but slowly you need to learn how to put this into sentences. Okay, so yeah, okay. Try to put your argument into sentences instead. Okay, so what about the next one? The next one is a lot of stuff inside there. So that doesn't matter. Okay, so what we also use chain rule. So we treat other stuff. Remember the partial derivative, we treat other variable as a constant. Okay, so what we get is 3xy, 3 constant, and then differentiate z with respect to x. Because we differentiate z with respect. Okay. So what are all these? So if we can factorize del x over del, yeah. Is it a product rule at the end? Huh?
Because y and z, I think cannot. Only x must be different to the x constant.
Is any x? Wait, let me.
Only y must be different.
Oh, right. Okay, so right. Wait, let me see. So let me see. So wait, only x. Oh, okay, we still got x. Oh, sorry, I stopped it z. Okay, so what's going on here? So do we treat y as a constant? Huh? Do we treat y as a constant? We treat y as a constant, right?
Yeah.
Okay, but we x still got x. Okay, still got x, correct. We only treat. So let me write down. You see, every time I don't write down reason, I most of the time is wrong. So okay, so we treat what? We treat y as constant. Okay, then x as a variable. Hmm. Fine. We haven't defined what's variable. Okay, don't want to get into this trouble again. So we only treat y as a constant. As a constant. Also, and also z is in terms of x. Okay, very good. So what do we get? So we get, what do we get? So we need to use product rule. What do we get after we apply product rule? Okay, how about let's pull out the constant here to make ourselves really comfortable first. So we get xz here, okay? So one is x, one is a function in x, right? Okay, now we do product rule. This. Why can we pull the constant out? Because the derivative is linear. So what do we get here? We get 1 times z, so it's that plus x times del z over del x. Okay, is it better now? Is it better? Okay, okay. So in the end, what do you get? So you just collect everything to the left hand side and right hand side. What you get is minus x squared plus 2yz over z squared plus 2xy. Okay. Okay. Similarly, you can try to check if you get try compute del z over del y, where you get minus y squared plus 2xz over z squared plus 2xy. Okay. Okay. So this is the implicit differentiation. So similarly, you can go to a higher partial derivative. You can do second partial derivative. So you can do fxs or fyy or fxy, fyx. So what does this mean? So fxs mean you do x differentiate with respect to x first, and then you differentiate with respect to x again. Okay. fxy, fyy means you differentiate with respect to y first, and then you differentiate with respect to y again. Okay. So what about fxy and fyx? So this is really a convention here. Okay. So what's the convention here? So the convention here is you do y differentiate with respect to y on the partial derivative with respect to x. Okay. So you do the inner one first and then you do the outer one. Okay. So this is the convention. Yeah, this is the convention. Okay. So be careful, be careful when you write this fxy and fyx. So our convention is do the inner one first and then do the outer one. Okay. Uh, should we do this? So let's do one. Okay, let's do one of them. So let's do fxy. Okay. So maybe one by one. Let's do one by one. So first step, what we do, maybe I just pass this. Please sign the attendance. So what's this definition here? By definition here, if fx differentiate with respect to y on partial derivative with respect to x. Okay. So this means we need to compute what is fx first. So we need to differentiate with respect to x. What do you get? So what do you get? You need to treat other variable as a constant. Okay. So other than x, you get ey for the first term, and then you get minus 1 over y plus x over y. The next one you get is y squared 3 times x squared. Is that right? Okay. Okay. Then what you do next, you can differentiate this with respect to y. So when you differentiate with respect to y, you treat other constant variable as a constant. E to the y. So here we got product rule again. Okay. So what's the product rule? We get u b prime, we get minus sine of x over y, and then plus b u prime. So what do I get? So I get minus 1 over y squared cos sine over 1 plus. So you treat x as a constant this time, so you get 6x squared y. Is it correct? Check my answer. This is correct one. Plus over sine over y. Plus 6x squared y. Okay? Yeah. Okay. So you differentiate both. Okay. So try find for the rest. I will put up the solution later. So try find for the rest. Yx and yy. Okay. Is it okay for this? Yep. What d? You mean this d? Oh, this d. Yeah. This d you cannot use because when you use this d, right, it means that the function only have that variable. When we put del, meaning partial. Why use partial? Because there might be more than one variable. They might have other variable than y or x. One. Okay. So whenever you see d, right, that means that function only has that variable. When we have del, have more than two. More than two? More than one. More than one. Yeah. More than one. Because every time you can only differentiate with respect to one variable. Yeah. So far doesn't have with respect to two variable one. Don't have this kind of thing. Yeah. Okay. 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 So the next is this theorem here. If both fxy and fyx are continuous, okay, if continuous, then fxy equals to fyx. This is very useful. Actually, this is quite surprising. You only have continuous partial derivative. Why they have to be equal? Interesting or not? A property of continuity implies some equalities. Right. So why is this true? Okay. I won't prove it. You can do it in your project if you want. Okay. Yeah. Yeah. So kind of an interesting result. Why, if when it is continuous, then they are just equal. This has a lot of implication. I think in complex also they use it. Complex analysis. Okay. So if more than two variables, you can have R3 to R function from R3 to R, R4 to R, R5 to R, Rn to R. Okay. So how you define it? So it's really the same way. Okay. You just if you differentiate along any coordinate, you just consider the increase of direction in that coordinate. Okay. So for example, if you differentiate with respect to x, the special function you want to look at is the increasing in the x direction. Okay. With respect to y, increase in the y direction. Increase in z, consider the z direction. Okay. It's really the same, no matter how many variables you want to consider. So higher order partial derivatives such as fxy, fyz are called a mixed partial derivative. So if you have more, then we'll call it if you differentiate more than one time, we'll call it a mixed partial derivative. Should we just skip these examples? This one we can skip because this is similar. So left. How about the next one? Are you confident to do this on your own? Or you want to try one example? Did you decide? Do you want to try? Or you can, confident on how to compute it. This is just how many variables? 1, 2, 3, 4, just the R4 to R. Are you guys confident or to try yourself? I will post out the answer later. If you don't get it and then you don't know why you don't get it, you still can ask. Then I will do it. You want to try it out yourself first, or you want to me show you one example? Show first one, huh? Okay, let's do the first one. Okay, so when they write del W times del X, right? Okay, so meaning we want to do del X first. After that, then we do del W. Okay, this is del W on the del X. Okay, so we got 4 variables here, but we want to differentiate only with respect to X. So we treat all the rest as a constant. Okay, we treat all the rest as a constant. So z is a constant, so we can pull the z up. And then we want to differentiate e to the w squared plus x squared plus y squared. Okay, so you differentiate exponential function, you just get that exponential function. But here you got a composite of exponential function and a polynomial function. So you need to do chain rule. Yeah. So what you do, what happened is you what do you get? So you get z times times 2x times e to the w squared x squared plus y squared. Okay. Hey, so if you want to write into this chain rule way, right? Okay, let me write out the chain rule way how you show it. Yeah, because last time you guys all confused, not all, most of you confused with how to use a chain rule. So how you really want to write it is differentiate with respect to x of w squared plus x squared plus y squared. And then what you do is differentiate the whole exponential function with respect to the w squared plus x squared plus y squared. This is what you really need to write down for your chain rule. Okay. Okay. So it is not x here anymore. So this is not x here. Okay, this is not x. This is the whole thing here. Somehow you are like doing the substitution stuff. Okay. Let's continue. So you want to differentiate this with respect to w again. Okay. So what do you get? So you also do a similar computation because everything in front of the exponential are all constant with respect to w. And then here we only have one occurrence of w squared. So what we get is 2xz of times 2w times e to the w squared plus x squared plus y squared. Okay? Is it okay? So what do you get at the end? 4xz w e w squared plus x squared plus y squared. Okay. So since if you prove that this function, if you prove that this guy is continuous and then this other guy is continuous, that should compute to the same stuff. Maybe you will know them without computing. Sometimes, okay, sometimes. Without computing, you can show that this second partial derivative is continuous. Then you will know that it doesn't matter you sort the order of differentiation. Okay. If the second order partial differentiation are continuous, then it doesn't matter how you sort the order. This is the theorem. Yeah. In terms of, you want to write in terms of big T? You mean you want or what? You want. You want to write in terms of big T, but I think you cannot do it. You can. I think the only thing you can write is 4x times T, right? But you still have x there. Unless you can write everything in T, then that will be okay. But you write half. We don't want half. Yeah, we don't. Huh? I mean, it's the same. I mean, okay. When you do things right, this must be a reason one. So why you want to do half? Okay, the reason is you want, but no one's care. You okay? I mean, right? All right. Okay. I mean, I mean. Sure. You can, but when you write this out, right? People look at it. So the reason is why you care. You just want, but you don't have a. But this simplification, okay, sure, you want to simplify it in this way, but like, is there any benefit of doing this? Look much better. So, what's the benefit of this looking much better? Huh? Feeling what? Feeling good. Okay. One of the indication is feeling good, but typically, okay, so typically, when we want to do simplification, we want to have some purpose. Yeah, we want to have some purpose. Let's say this everything, right, can just write in terms of T. This will give some ODE maybe or PDE. Okay. But if you can explain that this feeling good can imply something, then people will adopt it. If you're just feeling good and then this does nothing, then this won't carry on. This will just stop at you. This implication. Okay. Mm-hmm. Mm-hmm. I mean everything. I mean depend on what direction you want to differentiate. But this T here, right, is kind of complex already. You see, you want to split X, but you somehow still got X outside. So this when you want to do the next computation is create confusion, When you differentiate with respect to X, actually there's something inside T also. So I mean, yeah, right. If nothing. So I mean the reason what you want to do something, right? So what I want to say is the reason you choose to do something is because that thing can be used for the next thing. If it cannot be used for the next thing, you're just feeling good and you just stop here. So I mean this is the thing you need to figure out. This is the thing you need to figure out. How do you know? How do you find? You need to find. You cannot I mean, correct, right? You want, I mean, how to say? I mean, yeah, at some point you need to do the work. Yeah, at some point you need to do the work. You cannot just keep asking. You need to do the work. You ask until a stage, then you need to start working. So this is the place you need to start working. So can this fit to some other context or not? If can, then people will adopt this. If not, then it's just you pretty good. Yeah. Okay. So for now, yeah. But not allowed. It's not to say not allowed, non-standard for now. Non-standard. Okay. For the rest, if you don't want to continue this discussion, you can leave. But if those still want to continue, you can come to find me. We can continue.